Okay, so it's time for a final talk of our first day. We have Kewei Zhang from Beijing Normal University talking about Transcendental Okounkov.
Thanks for the invitation. It's my great honor to speak at this wonderful place. And also I'm happy to be the first person using slides to give a talk. Today my talk consists of three parts. I will first show you the background or the motivation for my project. I should mention this work, this talk is based on my joint work with Davas, Rablet, with Nystrom and Min-Chen Xia, who's also in the audience. And I will talk about the motivation for our project and then show you the main result. And finally, I will give a sketch of the proof. So, background. And when it comes to the relation between convex geometry and the algebraic geometry, there's a long history, right? So here there's a book named Convex Bodies in Algebraic Geometry. So there's a very famous topic called toric geometry, where you can study toric varieties using polytopes or convex cones. And also in toric geometry, if you want to compute some intersection number, then it's basically reduced to the counting of lattice points. So convex geometry is important in the study of algebraic geometry. Now, to show that my talk is related to the theme of this conference, I want to say a few words about Okounkov bodies and case stability. Well, in the study of case stability, Okounkov bodies play important roles. For instance, when you do computation for the expected vanishing order, if you know what that is, and also when you try to study test configurations, you need to look at the Duster-Matt-Heckman measure. You can understand this measure using Okounkov bodies as well. And also, when you are studying K-moduli space or Cayley-Ritchie-Soliton equations, you need to look at some T action on your variety, and in that case, Okounkov bodies also helps. So there are many applications in this field. And so let me first briefly recall the setup. So in my talk, I will always assume X to be a smooth projective variety for simplicity over the complex number, and let L be a holomorphic line bundle on the manifold. The volume of the line bundle is defined in the following way. You look at the growth of the dimension of global sections in ML, and you consider this quantity, and this limit sup is actually a limit, and this number is called the volume of L. And we call the line bundle big if the volume is bigger than 0. Okay. So big just means that from this definition is that you have lots of sections when M is large enough. So in birational geometry, big line bundles play important roles, but in some sense it's difficult to handle because its section ring is usually not finitely generated. So it's a nice thing if you can somehow have an intuitive definition for this volume. So this is where the Okounkov body comes in. In the work of 1996, Okounkov introduced a construction. I think he first did this construction for ample line bundles, but also it turns out that it works for big line bundles as well. So basically you fix a flag. A flag is just a chain of submanifolds whose dimension is decreasing. And so each yi is a closed submanifold of codimension I. If you are more familiar with analytic language, basically you can choose a local holomorphic coordinate system. Then the yi is just given by the vanishing of the first I coordinates. Given such a flag, you can define a natural map from the space of global sections to the lattice points in the Euclidean space. The definition is can be given as follows. in an analytic language, you can like think of sections in this space as locally as holomorphic functions. So you can expand it into Taylor series. It has infinitely many terms. Here I'm using multi-indices. And the map is simply given by this. You just look at the multiplicity whose term in this Taylor expansion is has the least, let's say, has the least degree in some sense. So here minimum is taken with respect to the lexicographic order. Okay, so this is one way to define this map. So for any non-zero section, you get a lattice point. Now, a more geometric construction is as follows. You consider a non-zero section here, and you want to define a map whose value is a lattice point in the Euclidean space. So you just define each component, right? The first component is just given by the vanishing order of S along Y1. Y1 is a smooth hypersurface in your manifold, so you can test its vanishing order along Y1. This gives you an integer, and so if this integer is positive, it just means that S is identically 0 along Y1. So in that case, you just somehow kill this order of vanishing. You just divide S by Z1 to the vanishing order of S along Y1. Then this gives you a global section in this space, which is not identically 0 along Y1. Then you can restrict this section to Y1, you get a section on Y1, which is non-zero. And then you can look at its vanishing order along Y2. Y2 is, again, a hypersurface in Y1. So you can continue this, and you can define all the remaining values. And eventually you get a map from the space of non-zero sections to Euclidean space. Okay. There's a very basic linear algebra fact which says that the number of lattice points you get in this way is actually equal to the dimension of your vector space. This basic fact somehow initiates the definition of Okounkov body. So because we remember that the volume of line bundle is defined using the dimension of this space, right? So now you can visualize the dimension using these lattice points. So somehow you just collect all these lattice points into a group, but you need to renormalize them. So if S is chosen from ML, then you need to divide these lattice points by M. This gives you a rational number, and you collect all these rational points in the Euclidean space, and then you take the closure. It will finally give you a convex body in the Euclidean space. From this construction, it's almost immediate that you can see that this body has something to do with the volume of L, right? So it turns out that you can show that, but of course you need to do some extra work. You can show that the Euclidean volume of this body is exactly equal to the algebraic volume of L, which is defined using space of global sections. So here I have drawn a picture. Basically, on each level M, you get a bunch of lattice points, right? But then you rescale them to the level 1, and you collect all these points together. This piece is the Okounkov body. So this volume, Euclidean volume, is can be shown to relate to the algebraic volume. A nice reference for this subject is a paper of Lazarfield and Mustata. And in their paper, they also have a question in the end. So the above story is for algebraic manifolds and algebraic line bundles, but in general, they ask, what if X is just a compact complex manifold? And in that case, and we need to replace line bundles by more general 1-1 classes on your manifold. So in that case, what happens? So this is their question. And in this direction, there's some previous work carried out by Deng, who defined a transcendental Okounkov body using some analytic language, which I will explain in this talk. And so basically, it's as follows: you're given a compact Kähler manifold, and you choose some big cohomology class. Well, Deng shows that there's a way to attach a convex body to this class, which we denote by delta. This typo should be delta of Kewei. And if the Kewei is the first Chern class of some big line bundle, then Deng showed that his body is the same as the algebraic body. So his definition is somehow a generalization of the algebraic case. And but the question he left with that, it is unclear if the volume of the Euclidean volume of this body is equal to the volume of the class. In his paper, he can show this volume equality when the dimension of X is equal to 2. But for higher dimensional case, that was left open. So in our recent work, we show that actually this volume identity holds in the Kähler setting. So let me first give you a version, a simple version of our main result in the Kähler case. So suppose you have a Kähler manifold, omega is a Kähler form, right? In that case, it's well known that you can compute the volume of your manifold. Here, by volume, I mean the Riemannian volume, in the sense of Riemannian geometry. In that case, you can just compute the volume using the top intersection number of your Kähler form. Right? This number actually only depends on the Kähler class, which is a 1-1 class in this cohomology group. And we can show that one can naturally associate a convex body to this class in the Euclidean space, and it turns out that the Euclidean volume is actually equal to this volume in the Riemannian geometry sense. So actually our results holds for big classes as well. So I will now explain what big class is in Kähler geometry. You can think of big class as some kind of degenerate Kähler class. So let's fix a compact Kähler manifold and also choose some cohomology class in this space. Let theta be a smooth representative. You see, here theta is chosen in an arbitrary way, and if theta can be chosen such that it is positive definite everywhere, then theta is nothing but a Kähler form. In that case, Kewei is a Kähler class, right? But in general, theta does not have any sign. It can be positive somewhere and negative elsewhere. That could happen. So in the rest of my talk, I'm gonna just assume Kewei is a general class, which is not necessarily Kähler, and we call this class big if it contains a Kähler current. What is a Kähler current? It's some weak version of a Kähler form. So it does not have any regularity, but in some distribution sense, it is positive, definite. So more precisely, you just consider all the L1 integrable functions, and you assume the function to be upper semi-continuous, and you want to, if this theta plus IDD bar phi is strictly positive in the distribution sense, then we call such a current a Kähler current. Okay, so if there is a Kähler current in this one class, we say that this class is big. So this is the definition. There's a close relation to the notion of big line bundle in algebraic geometry, because if L is a big line bundle, then the first Chern class is a big class in the above sense. This is due to books. Yeah. Now, here I have introduced the kilocurrent, right? But in practice, we want to use currents with nice regularity. So here comes the notion of kilocurrents with analytic singularities. These are closer to being a Kähler form. You can think of these currents as some kind of degenerate Kähler form, which is Kähler almost everywhere, but it can have some singularities along some subvarieties. So more precisely, the Maillet shows that if you have any kilocurrent, then you can approximate this current using a sequence of kilocurrents with nice singularities. So you can find a sequence of phi j such that phi j has very nice regularity. It's smooth almost everywhere, but there are some locus where it can be minus infinity, which is explicitly given by this way. So the locus where phi j is minus infinity is just given by the vanishing of these holomorphic functions. These phi i's as finite number of holomorphic functions defined locally, and yeah, this is the local form of this phi j. So any kilocurrent can be approximated using such a nice sequence. Okay, and by the regularization result of the Maillet, we now know that in a big class there are plenty of kilocurrents with analytic singularities. If you are an algebraic geometry, you should think of this as some analytic version of the Fujita approximation. In algebraic geometry, the Fujita approximation says that the big line bundle can be approximated using a sequence of ample line bundles, right? So this is like an analytic version of this fact. Okay. Now, how do you define the volume of the class? Right. So as I explained, there are plenty of kilocurrents with analytic singularities. So you can just look at the top intersection number. But remember that T can be singular along some subvariety. So you just forget about the singularity part. And in the rest of this locus, T is just a smooth Kähler form. So you can compute this volume. But the tricky thing here is that different T will give you different result of this integral. So you have to take the sup over all such T, and this will give you the number, which we call it the volume of Kc. And in the special case when Kc is a Kähler class, then the volume can be easily shown that it is just the usual volume of a Kähler class. And also another special case is that when the class is the first Chen class of a big line bundle, then the volume that's defined is equal to the algebraic volume. So a nice reference for this topic is the paper of Boxon. Okay. Now, so we have introduced the volume. Now we now want to introduce Okounkov bodies. This construction of Okounkov body is given by Yarden. He used the so-called Lidon numbers. So I use this slide to explain what Lidon number is. So recall any kilocurrent in your class can be written in this way. It's always theta plus IDD bar of some function phi. This phi can be negative infinite somewhere, and the Lidon number just measures how fast it approaches minus infinity. So take any point on your manifold, then the Lidon number of your current at this point P is just defined in the following way. Basically you compare phi with this function log distance squared. This term will go to minus infinity when x tends to P, right? So you just compare if you just define Lidon number in this way, okay? And for algebraic-minded people, you should think of Lidon number as follows. If you have a section here, let's say you have a global section, then you can look at this function. And then the little number of phi at some point p is just the multiplicity of your section at p. So there's this simple relation here. Yeah, so little number can be think of as some kind of generalization of this this notion, right? Okay. Now we can also define little number along a subrabride. So suppose you have y, a subrabride in X, then you can define the little number of t along y to be the inf of the little number at p, where p lies in y. This gives you a number, and you can also define the set where t has positive little number. There's a tricky thing you need to note is that for general current, the locus where it has a positive little number is not exactly equal to the locus where it is minus infinity, because phi can have zero little number somewhere, but it also attains minus infinity at this point. Because in that case, it just means that it goes to minus infinity really, really slowly compared to this guy. It could have like a log distance speed, right? So, but for our case, if you only consider about currents with analytic singularities, then this locus where it has positive little number is actually equal to the locus where phi is minus infinity. Okay. Good. So on the other hand, we also have the famous Sue's decomposition. This can be think of as this algebraic fact. So suppose you have a hypersurface in Y, and also suppose you have a divisor D on X, then you can also always decompose D into some part of Y plus some part of this divisor which does not contain Y, right? You can have this decomposition. For currents, you can do the same. You just for any Y, you can define a current, which is the integration currents along Y. The Y can act on any n-1, n-1 form in the following way. You just integrate this form along Y. And this gives you a current. And for any kilocurrent, Sue's decomposition says that you can just subtract T by some multiple of Y, and it will give you a current whose little number along Y just vanishes. So a priori T can have some little number along Y, right? But after subtract that multiple of Y, it has zero little number along Y. In that case, you can, if T has analytic singularity, it just means that T is smooth almost everywhere along Y. Then you can restrict T on Y, and you get a current on Y. This is very similar to what happened in the algebraic case. And so using this, you can define the so-called transcendental Okounkov body. So suppose you have a flag on your Kähler manifold, and then you just look at all the Kähler currents with analytic singularities in this class. You can define the following map from T to Euclidean space. You defined it component-wise. The first component is just a little number of T along Y1, and you subtract this amount of Y1, and you restrict it to Y1, and then you look at its little number along Y2, and you repeat in this way.
So sorry, are you assuming that your compact complex manifold has positive dimensional submanifolds?
Yes, this is a very good question. If you're right, given any Kähler manifold, it will happen that it probably does not have any submanifold. That could happen. In that case, you just do one small trick. You just pick any point you blow up, then you will get an exceptional divisor, which is a copy of P minus 1. In P n minus 1, there are lots of flags. So if the manifold does not have flag at all, then you just blow it up somewhere. Then you can build a flag out of it, and then you can do the following thing. Yeah. Yeah, that's a very good point.
You just look at the pullback class.
Yeah, you also pull back the class. The point is that when you pull back the class, the volume doesn't change. Yeah. So yeah, in this way you get a map from the space of kilocurrents with analytic singularities to the Euclidean space. And then you collect all these points here and you take the closure. It will give you a convex set in the Euclidean space. It can be shown that this is a convex body in Rn. And in Dunn's work, he proved that when X is a complex surface, then the dimension of this transcendental volume, the transcendental volume is equal to the Euclidean volume of the convex body. There's always some factor here which I'm not going to, yeah. So, and Dunn also conjectured that the same should hold for higher dimensions, but he was not able to do it. So in our recent work, we actually solved his conjecture. I will call it conjecture AN. Here N stands for the dimension. Okay, so basically you know what I'm going to do, right? I'm going to use induction on the dimension. Right? So this conjecture AN, it says that for the n-dimensional Kähler manifold, any big class has this identity. Okay. Yeah, this is the remark that I mentioned earlier. If X does not have any flag, then you just blow it up. Good. So I will now show you the proof. The proof goes by induction. Let's first look at the baby case. When n is equal to 1, then basically you just have a Riemann surface. In that case, everything is very simple. First of all, there's no such thing as a big class. Any big class on the Riemann surface is just ample. So in that case, the volume is very easy to compute. It's just the degree of your class. It's just this intersection number. Okay, and yeah, the class is Kähler if and only if the degree is positive, and volume is just the degree. And also, in this case, flag is simple. It's just a point on your manifold, and you pick a point, and you can measure the little number of t at a point. It turns out that in this case, the range of the little number is just an interval. It's from 0 to the degree of your class. So it's just an integral. Its length is equal to degree, which is the volume. So conjecture holds trivially in this case. Yeah. Now to go to the higher dimension, you need some extra piece, which is given by the following theorem. It says that this result goes to Witt-Nystrom. It says that to compute the volume of a big class, you can actually using some lower dimensional information, which is given by the restricted volume along some hypersurface Y. Okay, so this is a very key identity for our work. I mean, in algebraic geometry, there's also a similar identity. If you look at the paper of Lazar's field and Mustata, they prove this thing using Okounkov bodies. But in their paper, they already have this Okounkov body construction, and they know the volume identity. So from there, they can easily deduce this fact. But here, we do not know the volume identity, so you cannot go in that direction. So Witt-Nystrom used some deformation to the normal cone construction to prove this identity. Basically, he constructed some n+1 dimensional space, and he did some calculus on that total space, and eventually he proved this identity. Yeah. So we are going to use this, and here the term I'm integrating is the restricted volume. I will explain now. So so I should note that in algebraic geometry there are also restricted volume, right? But so here the version I'm showing here is an analytic version. So suppose you have a big class and you have a submanifold. Then the restricted volume is just defined in the following way. You look at all these kilocurrents with analytic singularity. Suppose it has 0 little number along your submanifold. Then you can consider the following integral. You just restrict t onto y, and you integrate on the locus where t is smooth. Then you get a number, but different t give you different number, and you need to take soup to define this restricted volume. It turns out that if C is the first trend class of a big line bundle, then this restricted volume is equal to the algebraic restricted volume in most cases. But in some subtle case, they can be different. But anyway, this is our notion here. And another warning is that this restricted volume can be strictly smaller than the volume of the restricted class. You see, here I'm just considering T from the total space X, right? But if you want to compute the volume of a restricted class, you need to look at currents on Y itself. These two different spaces can be different, so this inequality can be strict. Basic reason is that not every kilocurrent on Y can be extended to a kilocurrent on X. There is some kind of obstruction here. By the way, this extensional kilocurrent problem is also interesting in its own right. There are many people working in this direction. In our work, we also need to use this extension thing, which I will explain in a moment. So this is one thing. Basically, you can express the volume using some n-1 dimensional volume. Okay, but this volume is not equal to the volume of the restricted class, so there's still some subtlety here. So this is one thing here. Another thing is that for Euclidean convex body, what can we do about it? Well, this is simple. We just take the slices of this body. Let me draw a simple picture. For convex body delta, you just look at its slice. If delta is in Rn, then its slice is an n-1 dimensional convex body. It also has a volume, and you just integrate this volume along this from here to here, and then you get the volume of your entire body, right? This is simple, and yeah. So to show that this Euclidean volume is equal to the transcendental volume of your class, you just need to show that this holds, right? So the volume of each slice is equal to the restricted volume. If you can show this, you just integrate both sides and you get what you want, right? So here we pose another conjecture, which we call Bn. It says that any slice of the T-slice of the Okounkov body, whose its Euclidean volume is equal to the restricted volume of this class. Okay. So you can easily see that Bn implies An. This is almost immediate. So our next goal is to show that An-1 implies Bn. Right? If we can do this, then by induction we're done. Okay. Sure. So how do we approach Bn? Now there's a difficulty I mentioned earlier, which is that given any big class on your manifold and also given a submanifold Y, not every kilocurrent on Y can be extended. So this is the main issue here. But we can do something weaker. So here we prove an extensional kilocurrents result, which says that if C is a Kähler class, then we are good. Because if C is a Kähler, then given any submanifold Y here, and given any kilocurrent with analytic singularities, we can show that it can be extended to a kilocurrent with analytic singularities on Y, X. Sorry. This extension result is slightly stronger than the one proved by Collins and Tosadi earlier. They have a version which is not quite enough for our purpose. So in our paper, we gave a different proof, and our result is slightly stronger, which is just enough for our purpose. So basically, it's that when Xi is scalar, then we're good. But the thing is, for our class, even if we assume Xi to be scalar, we will eventually run into big classes because we want to show this identity holds for any t, right? So here t can go from here to here. So from the starting point, your class can be scalar, sure, but when t moves, the class will degenerate to a big class. So eventually you have to deal with big class. So yeah. To resolve this issue, we now need the third missing piece, which is the partial Okounkov bodies. I believe in Ming-Chen's talk, he will say more about this. So here I will just be very brief. Basically, it's like a Fujita approximation kind of argument. So you see, you have a big class, right? But you can always approximate using scalar class. And on the other side, when you have an Okounkov body, you can also exhaust this body using some sub-bodies, which are coming from bodies of scalar classes. So this is what partial Okounkov bodies give us. So choose any scalar current with analytic singularity. You can just think of it as a scalar form, but with some singularities, mild singularities along some subvarieties. After resolution of singularity, you can remove all these singular parts. So you can pretend that T here is just a genuine scalar form. Okay. Now, given such T, it can also give you a body, which is a subset of your Okounkov body. You just look at all these currents that is more singular than T. So it's like whose vanishing order is worse than T. Okay, you look at all these T prime, and you look at all their little numbers, and you take the closure. So this gives you a subset of your original Okounkov body. Basically, your Okounkov body can be exhausted by such subsets. Okay. Now we have the third conjecture, which says that this the volume of this partial Okounkov body is exactly equal to this integral. Okay. So suppose you have this conjecture, then you take sup on both sides. So here it gives you the volume of your class, and here it gives you the volume of your body. Okay. So the entire body. So if we can show this, then we're also good, right? So from here we know that AN and CN, they are equivalent. Okay. So what do we have here? Now we have a bunch of conjectures, right? A, B, C, which we don't know how to prove. Then we play the game. We see which implies which, right? So from our discussion, we know that A1 holds for trivial reason, and we also know that we also know that AN and CN are equivalent. So there's one implication that I have already explained, right? So CN implies AN, but the reverse direction also holds, because this is basically saying that for scalar classes you have AN. So AN also implies CN. So A and C are equivalent. And also I have shown you that BN implies AN, right? So what remains to be shown is that Cn minus 1 implies Bn, right? if we can show this sentence, then we are done, right? So what is Cn minus 1? It says that for n minus 1 kilomanifolds, you always have this identity. But this identity basically is, as I explained, is saying that for Kähler classes, you have this identity. But Kähler class is good because for Kähler class we can apply our result, right? We can apply our extension of Kähler currents, which basically says that, roughly speaking, it says that this strict inequality is an equality. Okay. So in that case, then we can just apply induction, and then we use with Nystrom's formula, we will get our desired volume identity. So this is the rough philosophy here. I'm not going to show you the detail of the proof because it is kind of technical, so it will make things ugly. So I will keep it this way. So let me wrap it up for you. So what have we done? We have shown that A1 holds, right? And AN and CN equivalent, and Cn minus 1 implies Bn. This is the most non-trivial step in our work because we need to apply the extension of Kähler currents result to deduce this step. And then Bn implies An is also standard. After you combining these four sentences, you will see that actually An, Bn, and Cn, they all hold true. Okay. So I think this is so much for my talk.
Thank you very much. Any questions?
How do the Okounkov bodies depend on this flag? So if you choose a different
Yeah.
flag,
This is a very good question, and also, yeah, the body will change if you use different flag, and it changes in some, I would say, unpredicted way. I would say when you use different flags, the shape can change dramatically, but the volume still remains the same. Yeah, but the shape of the body actually can reflect some positivity property of your class. If your class is, let's say, Kähler, then it will always, let's say, so for a Kähler class, no matter how the shape change, the body will always look like something like this. It will always contain the first, this simplex, I should say. Yeah. So different bodies may share some similarities due to the positivity of your class. But once you are away from this part, then the shape can change in many different ways.
In toric case, you can also compute the equivalent intersection. Not only intersection, but you can also consider, for instance, T equivalent intersection, and you can compute it using toric convex moment polytope. And I wonder if you can do similar things using.
Yeah.
I think I will.
Yeah, I think maybe Mingchen has some words to say. Yeah, because in that case, I think this is a subject still needs to be developed. In the transcendental case, there's not very good notion of intersection number. So how do you compute intersection number using Okounkov bodies? I think this is still an open question. Yeah.
This is another question. If you consider ample N model and consider test constellation of X and L, then well, I think you can construct some convex function on Okounkov for it, right? And,
Sure.
We can do similar things.
Yeah, sure. Yeah, this is what we can do. You can in transcendental setting, you replace test configurations with geodesic rays or test curves. Test curve is the Legendre transform of geodesic ray. In that case, each test curve will somehow give you a concave function on your Okounkov body. This is something, yeah, analog with the algebraic case.
Maybe it uses
Yeah, I just sorry.
But if you just start off with the test configuration in the Kewei category, do you do anything?
You mean just look at test configurations in Kewei Zhang? In that case, I suppose there are some special properties for the geodesic rays associated to the test configurations. Yeah, you should have some kind of characterization when the geodesic ray is coming from test configurations. There should be some theorems about that. But what I'm saying that one can actually treat any geodesic rays, take their Legendre transforms, and you can study even concave transforms of these functions on Okounkov bodies, and yeah. But still, this is a subject that I think there are a lot of things to be done. Yeah, yeah, maybe Ming-Chen will say more about this.
Is there an algebraic version of the partial?
I think yes. So you like somehow you like in the construction you just consider those sections with some a priori vanishing order along some sub-array, and this should give you a partial Okounkov body, I guess. Yeah. I'm not sure if anyone has written down that explicitly. I think so.
I have a question. When defines the volume of B class, we say it is an infimum of the volume of current.
It's a soup.
Yeah, true.
Yeah.
But is it attachable? I mean, is there a special current maybe?
In general, no. No. Yeah. But if you use another language, there's something called the currents with minimal singularity. That current can attain the volume, but that current is not of analytic singularities in general. If you just use currents with analytic singularities, you have to take soup, and usually it's not attainable.
Any more questions? Okay, let's thank Kewei.